So we will wait for a couple of more minutes. So people are coming. A few more minutes will wait.
Wait a few more minutes, or shall we start?
Yeah, we can start. Yeah.
We can start. Okay.
Yeah. So, hello. Welcome everyone to the third day of the fourth Big Math Conference. So, the first talk of the day, the speaker will be introduced by Professor Karantikar.
Yeah. So, our first speaker today is Professor Arup Bose from Indian Statistical Institute, Calcutta, or Kolkata, as it is now called. Let me mention that I have known Arup, or both of us have known each other for over 40 years, since we were students at ISI, Calcutta. He's going to today speak on spectral measures of empirical autocovariance matrices. Arup.
Thank you, Rajiva. So as Rajiva pointed out, that we go back a long time, and it's always nice to hear his voice. Physical meetings will happen hopefully soon. So my plan today is to talk about spectral measures of empirical autocovariance matrices, but the bulk of the talk will be addressed towards trying to attract people, students to this topic. So I will go back a little bit in history and try to give you some idea of the different kinds of matrices that have been dealt with in the literature, and then eventually come to my couple of main results that we have been working on recently. So what is a random matrix? A matrix, all whose entries are random variables. That is, the entries are drawn according to a given joint probability measure. So you might have patterns within the matrix, or you might have IID, or independent identically distributed variables in the matrix. The study of random matrices has become important in mathematics, for example, in operator theory, non-commutative geometry, non-commutative probability, and of course in statistics, inference for high dimensional data. That's where I got interested in. So you look at random matrices whose dimensions are large, or in other words, mathematically they are going to infinity. In particle physics, in wireless communication, and the development of the 5G network that we are getting used to, there was a heavy use of random matrix theory in developing that the network. Because of the importance of the subject, there was a new journal which was started in 2012, Random Matrices Theory and Applications, which is published by World Scientific. And that has a very strong editorial board from looking at different aspects of random matrices. So here is the outline of my talk. As I said, I'll give some historically important random matrices and results, but not in details. And then I'll talk about high dimensional time series and sequences of sample autocovariance matrices. And I'll mention a couple of results on for the bulk of the symmetrite sample autocovariance matrices. I'll explain later what I mean by the bulk. And it is known in the literature, people who have worked in random matrices, that when you have a symmetric matrix, it's easier to deal with its distribution compared to the non-symmetric case. And so I'll also mention a couple of results on the non-symmetric sample autocovariance matrices. Okay, so here's example one. This is how it's for statisticians. This is the basic example of random matrices. So you look at the 2x2 contingency table, for example. So you might have two traits, for example, whether you are a smoker or not, and whether you have a cancer or not. So you have the counts on the different rows and columns, depending on whether you answer yes or no to these traits. So that's like a random matrix, because when you collect the data, all these elements are going to be random numbers. Example two, the data matrix, where each column is one observation of dimension p, and there are n such vector observations. So you can think of each of these columns as a p-dimensional, an observation on a p-dimensional variable. Of course, there might be dependence within the columns, there might be dependence between the columns, and so on. Usually p is fixed and the number of observations n is allowed to grow. But in high dimensional statistics, the dimension p, the vector of the length, is also assumed to be large. Example three, the sample covariance matrix. That's a bread and butter for people who do multivariate statistical analysis. So I talk about the unadjusted PYP sample covariance matrix, which is nothing but x star. So throughout the star will denote the conjugate transpose. Most of the cases I have x, the elements of x are real, but they can be complex in some cases. So you look at the data matrix x and you look at x star, and you average it out because you are multiplying rows and columns. So that's the sample covariance matrix. When the entries are Gaussian, S is called a Wishart matrix. It goes back to 1928. And in that case, the joint density of the eigenvalues can be calculated, and they are used for statistical inference. Also, when P is fixed and N is large, the central limit theorem arguments can be used to study the large sample properties of this matrix S, including the asymptotic normality of the eigenvalues. And this is what statisticians would normally use when you have fixed dimensions to study multivariate data. For example, principal component analysis and etc. When P is also large, the behavior of its eigenvalues is very different, which has two parts to it. First, the standard methods of analysis do not work anymore. And the second is that what happens to the behavior of the eigenvalues, and P also becomes large along with N. And then we have this Martingale-Pastel law for the bulk of the distribution, or the different Tracy-Vidom laws for the extreme eigenvalues of this matrix. Some other random matrices that have been worked on and have been popular for various reasons, or have been important, the Wigner matrix, which goes back to approximate. So these dates are approximate. 1955, which arrives in nuclear physics. The Topli's matrix with IID entries. It is related to, so Topli's matrices come up in time series and also in operator theory. The Hankel matrix. I'll give you simulations of these later on. The IID matrix, so I'll call it the IID matrix when all the observations are IID, and usually it's a square matrix, but you can have a non-square IID matrix also. Of course, it's very important in non-commutative probability. The beta matrices, which are sort of generalizations of the sample covariance matrix. And then there are this autocovariance matrix, on which I will focus a bit towards the end of the talk. So what is it that we should study for random matrices? Of course, matrix is a linear transformation and whose features are captured by the behavior of its eigenvalues. Now, the bulk behavior of the, so these are some of the things that are studied. For example, the bulk behavior of the eigenvalues. For instance, the famous semicircle law, the Martingale-Pastel law, they have arisen. by studying the behavior of the bulk behavior of the eigenvalues. You can also study the extreme eigenvalues, and as I mentioned, you can get the Tracy-Widom laws or the Gumbel law for extreme eigenvalues of different random matrices. This is not too many results are known for extreme eigenvalues of random matrices. The Wigner matrix and the sample covariance matrix, of course, have been well studied, but for the other matrices, there is a lot more to learn. One can also study the gaps between the eigenvalues, which is connected to determinantal point processes. Then finally, you might have more than one sequence of random matrices. So in that case, you would like to study the joint behavior of several sequences of random matrices. And that's when you get into non-commutative probability, because matrices are non-commutative objects. And so when you have more than one sequence of random matrices, you naturally have to deal with variables which are non-commutative. And there is this very important notion of free independence that comes up when you study joint behavior of different random matrices. And then, of course, last but not the least, applications. A lot of applications are being done of these results that are appearing, theoretical results in different areas of mathematics and also other sciences. So I have been mentioning bulk. So let me define what I mean by the bulk of a matrix. So this is the concept of the empirical spectral distribution. So suppose that R is a PYP random matrix with eigenvalues λ1 to λp. Then its empirical spectral distribution is nothing but the probability distribution, which puts mass 1 over p at each of these eigenvalues. That is probability. You think of a random variable x, which takes the values λ1 to λp with equal probability 1 over p. This probability distribution varies from sample to sample. So if you have a random matrix, then all these eigenvalues are of course random. And so it is a random probability distribution. You can also think of the corresponding histogram of the lambda i's. So that is like a random probability distribution. Okay, and then you have the concept of the limiting spectral distribution. So you look at this empirical spectral distribution, and you assume that the dimension p is running off to infinity. And then what happens to this probability distribution, or the random probability distribution of the eigenvalues? So if as p goes to infinity, this random spectral distribution converges weakly, and this convergence could be in different probabilistic senses. So either in probability or almost surely to given probability distribution, then the limit is called the limiting spectral distribution. Of course, the limit can also be a random probability distribution, but in our talk, all of these limits are going to be fixed probability distributions. So this is called the convergence in the bulk, since any finite number of individual eigenvalues do not matter for the limit, because p is going off to infinity. So that's why people say that we look at the bulk limit of the bulk distribution. Okay. So my fourth example, the Wigner matrix. I mentioned Wigner matrix, so let me define that. So it's simple and the easiest matrix that you can think of. So all the entries are assumed to be IID, except that you have symmetry in the matrix. So it's a symmetric matrix with IID entries. And you can, of course, have variations of this IIDness, or what kind of distributions you allow, and whether these distributions depend on the dimension n. They can keep on changing, like a triangular array and things like that. And here is simulation of the Wigner matrix. This is 15 realizations of a scaled Wigner matrix, and you can see that I've used the Bernoulli entries here, but the limiting spectral distribution in this case is universal, meaning that, so universal means that the limit does not depend on what kind of parent distribution you use to generate the matrix. So the limit depends only on the variance of these entries. So usually you standardize and make it variance 1. So this is precisely the semicircle law that I was mentioning, which is also known as the free Gaussian law for other reasons in non-commutative probability, which I cannot go into. Okay, example 5. This is the Toeplitz matrix, and this is connected to the Toeplitz operator, and there's a very long history in mathematics. So what happens here is that each diagonal has the same value, as you can see in the display. And moreover, in this case, I have assumed that it's also a symmetric matrix. In general, they need not be symmetric. So here is what happens to the Toeplitz matrix, the symmetric Toeplitz matrix when it's simulate. And again, the limiting spectral distribution is universal. So here you can see 15 different graphs, which also shows you that the limit distribution exists in the almost shear sense. There is not much variation between the different graphs, the different realizations of the matrix. And so it is known that this distribution is unbounded, but it's not Gaussian. It has a sharper peak than the Gaussian. But it has also not been identified what is, so nobody knows what this distribution actually is. Not known in any kind of closed form. Similarly, the Hankel matrix puts the observations on the anti-diagonal as equal, as you can see. So first you start with x0, then in the first anti-diagonal you have x1 and so on. So this gives rise to the Hankel operator. It's also actually related to the Toeplitz operator in a sort of non-linear way. And here is what how the simulation of a Hankel matrix looks like. So again, I have 15 individual realizations here. So each curve is based on the 400 eigenvalues. And I have used IID Bernoulli and this, but you get the same kind of picture if you had used any other kind of distribution. Again, the limiting spectral distribution is universal. And you can see from the picture, it's not unimodal. One can prove easily that it's not unimodal, but there is interestingly no proof yet that it is indeed bimodal. And just like the Toeplitz matrix, its distribution has not been identified. Okay, example 7 is a sort of an easy matrix, but it's an important matrix in many fields. So that's why I decided to show this. So the circular matrix, you have the first row x1, x2, xn, and then you circulate the elements of the first row in the other rows by shifting one place right. So next row is xn, x1, and so on. Of course, this is a non-symmetric matrix, so its eigenvalues in general will be complex numbers. And this is how it looks like in the simulations. So again, the limit is universal, but it's now a bivariate or a complex Gaussian distribution. Okay, next example, this is sort of a continuation of example 3 that I did earlier. So the sample covariance matrix simulation. So again, you can see that there is a limiting spectral distribution. If you simulate, you get same picture, but the limit distribution now depends on the ratio p by n, as it should, because you see if the variance covariance matrix dimension is p, but the column dimension is n. So if n is smaller than p, for example, then you have a lot of zero eigenvalues. In this case, p by n is 0.25 and p by n is equal to 0.5. I have been given you 2 cases. But if n is if p is larger than n, then which are not displayed here, then you'll get a mass at 0 also, because you'll get that many zero eigenvalues. So again, this is the limit is universal. If this limit distribution is known as the Martingale law. And the limit depends on the ratio p by n. So you assume that p by n goes to some constant y. And it's also known as compound free Poisson law because it has connections to free probability. So in next example, which is the IID matrix. So you have this non-symmetric square matrix, all whose entries are IID with variance 1. Again, you can have variations in these assumptions. I don't want to go into those things. And this is how the simulation looks like. So the left side is a standard normal, and the right side is the Bernoulli. You can see that you get the same picture, and it's all dense, and there is no gray areas, which means that the distribution is uniform on that disk with, of radius 1. And again, the limit is universal. This is a very hard result to prove. So next example, the autocovariance matrix. So this is where I spend a little bit more time. So suppose that x1, x2, xn, etc. is a real valued mean zero stationary Gaussian, stationary stochastic process. Then its autocovariance sequence is defined as gamma h, which is expected value of xt times xt plus h. Of course, I'm assuming that the variances are finite. And because it's a stationary process, this expectation depends only on h and not on t. Now, if I look at the dispersion matrix of x1, x2, xn, you can see that, for example, the covariance between x1 and xn is going to be gamma n minus 1, which sits at the extreme corner of the matrix sigma n. Or if I look at the covariance between x1 and x0, that will be gamma 1, which is the second element in the matrix, and so on. So very soon you realize that this matrix here has a nice Stokes structure. So you have gamma 0 on the diagonal, gamma 1 on the first diagonal, and so on. And so this has a nice Stokes structure. The corresponding sample version of this, where you replace those gammas by their estimates, is given by the matrix capital gamma n x, which is gamma hat of the mod I minus j. So this now becomes a random matrix. You are assuming that the xi's are IID. And this is what happens for the sample autocovariance matrix when you assume that P is 1. So the limiting spectral distribution exists. So here the dimension n goes to infinity. P is fixed, but you're looking at, let me just go back a little bit here. So you're looking at this gamma n x, which is an n by n matrix. And this has the same structure as this sigma n, but you have replaced this gamma i's by their estimates. So that's a random matrix. Okay. So it's known that the limiting spectral distribution exists. This was joint work with Anirban Basak and Sanjan Shen, both of whom worked on this while they were master students. I think Sanjan may be in the audience today. Maybe also Anirban is in the audience, I don't know. So the limiting spectral distribution exists, and its properties are not known, but the spectral distribution is connected to the spectral density of the process, as it should, and it's unbounded. So this is in very great contrast with the sample covariance matrix. Remember that the sample covariance matrix was the LSD was the Marchenko-Pastel law, which is actually bounded between 0 and some number which depends on the ratio P by n. So in contrast to that, here the limiting spectral distribution is actually unbounded. So now let us look at what happens if I have vector valued observations. So that was talking about earlier slides. We're talking about when xt was a real valued sequence. So now suppose that xtp is a p-dimensional vector valued time series. I'm going to impose assumptions on this time series soon, different kinds of assumptions. So for a real valued time series, of course, we had already seen that there's only one sequence of autocovariances, namely you look at the xt and lag xt plus h and take its expectation. Now for every lag h, you have this vector. So xt is a vector now, xtp. So now instead of the autocovariance gamma h, you have an autocovariance matrix of order h. And so that is really xt plus h star. So for every lag, you get a matrix. And so the sample autocovariance of order I of xt is the p by p matrix now. So earlier I had xt times xt minus I. Now I have a vector. So I take a star. And this is my gamma I hat. So this is the sample autocovariance matrix of order I. And I could, of course, be running from 0 up to n minus 1, but you look at, you fix I at a finite number and look at its properties. So the broad goal here would be to study the properties of these sequences, including the joint convergence, as p and n both go up to infinity, and they can go up to infinity in different ways, like p by n can converge to a constant, or which is non-zero, or p by n can converge to 0, and there are different situations. And we seek to study its properties, and then see whether we can apply these results to, in particular, to statistics. So we have made some progress, and we have been working on this since 2013 or 14, around that. So Monica Bhattacharjee has written a PhD thesis on this topic in 2016. And since then, I'm also working with Walid Hutchin, and we were supposed to work a little bit more, but due to the pandemic, we got delayed, and our projects have suffered seriously. So I want to make some remarks here. First of all, if the entries are IID, then gamma 0 hat. So when you have no lags, it's really, if we go back to the slide here, so gamma 0 hat will be xt star, right? Because I is 0. So then you get back the sample covariance matrix. Even in the all IID case, when all the entries are assumed to be IID, the sample autocovariance matrices of other orders have strong dependency in the entries, as you can see, because you are mixing up xt and xt and the lags. Except for I equal to 0, all these matrices are non-symmetric. And it is, of course, known that non-symmetric random matrices are very hard to analyze. And one of the basic reasons that they are hard to analyze is that is because if you take a non-symmetric matrix and you perturb one of the entries, then the corresponding eigenvalues are not sort of smoothly well behaved with respect to this perturbation. So that is what makes these non-symmetric matrices very hard to analyze. So there's a way out. One way is to symmetrize this, whatever non-symmetric matrix you're dealing with. So for example, you can look at the singular values. You take the product of gamma I star, or you can add them and make that's an additive symmetrization. That, of course, entails from statistics point of view, entails loss of information because you're not dealing with the original sample autocovariance matrix, but some function of it. So it was important to try and see what happens to the original matrices without the symmetrization. I'll come to the results soon. Now, for wireless communication applications, it is also important to consider a case where XTP are complex valued random variables. So points to note, some sort of structural assumption needs to be imposed on the variables XTP, which I have not imposed yet. I just said stationarity. That's not enough to get to the limiting spectral distribution of these matrices. And of course, those who have worked in this area would know that, realize that the Gaussian case is expected to be easier. In other words, when you assume that further that the entries have the Gaussian distribution compared to the general case. Okay, so here is my first model, the high dimensional time series model. So I'll call it the MAQ model. So this is exactly like the usual MAQ model for real value time series, except that now you are allowing vectors. So xt is a vector of dimension p. The psi j's are matrices of dimension p, the square matrices, and epsilons are also vectors of dimension p. And I assume that they have mean zero and variance covariance matrix IP. If they don't, then things are really much more complicated, and we can do something, but complete results are not known. Okay, and the psi j's are coefficient matrices with suitable assumptions on their joint convergence, meaning that they should converge. For the more technically minded audience, they should converge in the tracial sense, or in other words, you take the products of these matrices, finite products, any polynomials, and compute their trace, they should converge. That's a minimal assumption that you would anyway need for the convergence of the eigenvalues. And P is supposed to be a function of n, such that P by n goes to gamma, where gamma could be anywhere between 0 and infinity. And MA0 would be the IID process. So when I assume that all the psi j's are 0 except psi 0, which is identity, then xt is the IID sequence epsilon t. So I refer that as the MA0 or the IID process. So here are the limit results for model 1. And as I mentioned, this is joint work with Monica, and all of it appears in her thesis. And then we also wrote it up in the form of a book, adding some more stuff there. And if you're interested, you can look at the book. The limiting spectral distributions for symmetrized autocovariance matrices of all orders exist, but it is not possible to write them down explicitly. So this is a very strong generalization of the Martingale postula. because here you are dealing with the all kinds of autocovariance matrices, and gamma 0 is a special case. These LSDs can be described in terms of free variables. And the joint partial convergence also holds when you have several independent time series. So instead of having one time series xt, I can have xt and yt, and I can have the corresponding autocovariance matrices from these two sequences. And those matrices will also converge jointly. The trace of any combination of the sample autocovariance matrices is asymptotically normal. So if I take any polynomial in these autocovariance matrices, a finite degree polynomial, and calculate its trace, then that trace has an asymptotic normal distribution after appropriate centering and scaling. So that is important for statistical analysis. But what is the technique of proving these results? Well, what we do is we embed into IID matrices. So these autocovariance matrices have the structure, right? The structure that I mentioned here in equation 4. So using that, if you, for example, if you look at xt star, then it will involve the matrix epsilon star. So you use those to embed these matrices into IID matrices, into polynomials of IID and deterministic matrices. And then once you have polynomials of IID and deterministic matrices, then you can use the moment method, because you assume that you are looking only at the symmetrized cases. Then using the moment method along with asymptotic freeness properties of IID and deterministic matrices, one can get these results. One can also compute this limiting Stiglitz transform, giving rise to very complicated equations. So to sum up, this is basically a moment method, even though after you prove the convergence, you can get the Stiglitz transforms also. Working directly with the Stiglitz transform is also possible, but then in that case you have to assume something extra on the matrices sideways and so on. So, for example, that they are simultaneously diagonalizable. So, but on the other hand, if you use the moment method, then you can avoid those extra conditions. Okay, so here is a glimpse of what you could do with such results. For example, if I have the IID process, so suppose xt is epsilon t, and so here I have plotted 4 graphs actually, and they all get superimposed on each other because they have the same limiting distribution. That's not very hard to guess. Let me go back here. No, maybe I'll explain it with the slide itself. So for example, if you look at gamma 1, so that's like summation epsilon t minus 1. If you look at gamma 2, that is summation epsilon t minus 2. Now think of the usual real valued case. So if I have summation epsilon t minus 1, that epsilon t is an IID sequence, then that's of course a Martingale, and we can use the Martingale convergence theorem to prove its convergence to the normal distribution. Similarly, if you look at epsilon t minus 2, that is also a Martingale, and you can realize there is covariance structure, and epsilon t minus 1 covariance structure of that really is the same. So you really get the same limit, okay? Which is in the null case where you assume that epsilon t is IID. So this is no surprise that you actually get the same curve when you look at all these before different orders sample autocovariance matrices. So basically, you're looking at singular values here. On the other hand, if you assume that xt is not IID, which is the next picture here. So if you assume that xt has one first order dependence, so epsilon t plus ap epsilon t minus 1. For ease, I have taken AP to be some constant times the identity matrix. Then, of course, if you plot again the same 4 curves, then one of them separates out. The one that separates out is the gamma 1, and that separates out because you have order 1 dependence. In other words, you can very quickly graph the singular values, and that will tell you what order of dependence you have in your model. Okay, so having said that, now let me go to the non-symmetric case. So here is a simulation for the MA0 case. So I have gamma 1 hat. I decided to give the definition once more. So I have 1 over n summation xt minus 1 star. So that's the sample autocovariance of order 1. Remember that I'm assuming that the epsilon t's are IID and x is equal to epsilon t. So I'm in the IID situation, but the entries in this sum are dependent on each other. And this is how the simulation of the eigenvalues look like. So on the left, you have n equal to 500 and p equal to 250. So p by n is half. And on the right side, p by n is 1. So of course, the distribution depends on the ratio p by n. And these pictures tell you that probably as n and p go to infinity, there is a limiting spectral distribution. And you can imagine how that this would be hard to prove. Go back to the IID matrix. So if I have X as the full IID matrix of square IID matrix, and the spectral distribution of X converges to the uniform distribution on the disk, and that's pretty hard to prove. Okay. So for non-symmetric matrices, spatial convergence does not yield existence of the limiting spectral distribution. From the work with Monica, the tracial convergence of all these matrices are guaranteed. So you look at any polynomial, we can say that the trace converges, but that is not enough to guarantee the existence of the limiting spectral distribution. It's like trying to prove the convergence of complex random variables by using the moments. If you use the moments, then you have to use the complex moments also. It's not enough to look at just powers of the variable. One of the major steps in the proof of any non-symmetric matrix is to establish suitable bounds for the smallest eigenvalue of the matrix. So this is a very technical area, and those who know that this is the crux of the matter, and those who don't, it's very hard to explain in a talk why the smallest singular value is the behavior of the smallest singular value is important to get to the bulk of the matrix. Okay, so let me give you the assumption, but I will not be very precise. You have to go back to my papers in the archive or the published papers to get a sense of the assumptions. But I'll just sort of hand wave what kind of assumptions we need. The P by N data matrix X consists of IID random variables with a non-trivial complex part. So unfortunately, we got stuck with this, but Walid is from wireless communication. So he was happy with what we got, and we could not get rid of this assumption. In other words, we could not assume that the entries of X are real because of the method, the technique of the proof that we have used. And with appropriate moment conditions. This is fine for applications in wireless communications and signal processing, as I mentioned, but not acceptable for time series applications if you have a real value vector time series. This assumption is due to the application of a variation bound as a tool in one of the steps in the proof. Okay. So that is essentially the assumption on the variables. Again, to stress, the X has all IID random variables, and I now have will introduce a matrix, an auxiliary matrix A, and you'll soon see why I need that. So this is a notation for the singular values of any matrix M, and I assume that the smallest singular value of this deterministic matrix A and the largest singular value, they are bounded away from, away from 0 and infinity. Remember that the dimension n is going off to infinity. The identity matrix, of course, trivially satisfies this assumption, and the circulant matrix, which is of that above form here. So here is 1. You start with 1, and then you circulate that. That is also satisfies this assumption. The limiting spectral distribution of this circulant matrix is uniform distribution on the circle of unit radius. That's not very hard to see because you can explicitly calculate the eigenvalues of this circular matrix. Okay. Then here is a general smallest singular value result. So suppose norm denotes the spectral norm of the matrix. Consider the random matrix X A X star minus Z times the identity matrix, where Z is an arbitrary non-zero complex number and IP is the identity matrix. And suppose P by N goes to gamma, which is not equal to 0, then the smallest singular value of X A X star minus Z there's a scaling here which I've forgotten to write. So it's all scaled by n. On the set where norm x is less than or equal to c has this upper bound in terms of t and n. Now, it is known that because of the IID LSD, that norm x less than or equal to c happens with probability 1. Remember the simulations I showed you that all the eigenvalues lies within the unit disk. So that extra set norm x less than or equal to c is not a problem. With large probability that automatically happens. And so this result controls the smallest singular value of x a x star. The right side bound is not not sharp, but it was good enough for our purposes. And I again stress that we do not have the result for matrices with real entries. My x has entries which have non-trivial complex part. Okay. And so to describe the result, I will put up the result, but it has some big formulas, but it's okay. So the let g be this function y over y plus 1 times 1 minus gamma plus 2y whole square, where gamma is the ratio p by n. G is of course a cubic polynomial. It's analytic and increasing in the interior of an appropriate interval. And so here is the theorem that I proved with Walid Hachem, which was appeared in JMA. Under the assumptions, the limiting spectral distribution of xt minus L star. So L could be anything here, strictly positive. As I mentioned, the lag, the order of the lag really does not matter in the IID case when you have the MA0 case. The limit spectral measure mu is rotationally invariant on C and can be written in terms of the function G. And its support is within this disk. So it's very much like the uniform law that we have seen. So there's a disk of finite radius on which it is supported. And when gamma is bigger than 1, the support is a ring together with a point 0. As I mentioned, there can be a 0 eigenvalue and there is a separation. So there is mass at 0 and there is a gap, and then you have a ring on which the distribution sits. The radial distribution Fr has a positive and analytic density on the open interval, whatever. And this density is bounded if gamma is not equal to 1. If gamma equal to 1, then the density is unbounded, except everywhere except when Fr, where R is converges to 0. Okay, so so that is what happens when you have the IID case. So here is a simulation, as I mentioned. So if you look at the right side, there are some eigenvalues in the center, and then there's a gap, and then you have this ring. And if you so that is then p by n. So sorry, capital N should be p here. So that's a typo. So here p by n is so n is much larger. And here I think I messed up. I switched anyway. Doesn't matter. So in one case there are no 0 eigenvalues. In the other case there is a mass at 0. Okay. Model 2, instead of MA0, which is you can think of as the null hypothesis case, you want to test whether a given time series is a white noise or not. That's the null hypothesis. We now assume that XTP is a stationary Gaussian process. So that's where we move to the Gaussian assumption. As I mentioned right in the beginning of the talk, Gaussianity helps, and we have not been able to relax this condition. It was already a heavy work, heavy lifting, even in the Gaussian case. We assume that the spectral density of the process is well behaved. For example, it is bounded away from 0 and infinity. But I'm not assuming IIDness here anymore. So, but I'm assuming it's only stationary Gaussian, and so it will have automatically have a spectral density. So I have to assume something on this that spectral density. I will not give you all the assumptions here. So this is how the singular value now behaves. So essentially same kind of result that we had earlier, but now the technique of the proof is a little different. You heavily exploit the case that we are in the Gaussian case, and you have a spectral density. So the spectral density comes up in the arguments repeatedly. And there is another result on the technical result on the spectral distribution. So I need to control these others to some spectral, sorry, the singular values in another regime also. So here the bound is exponential. Okay, so this is my final result. So let mu p denote the empirical spectral measure of, sorry, that's the type of capital gamma hat L, meaning the autocovariance matrix of lag L. Suppose these assumptions hold, then there exists a tight sequence of deterministic probability measures mu p on C, such that for each bounded and continuous function f, integral f d mu p. So the first integral is with respect to the empirical spectral distribution. The second integral is with respect to bold phase and normal phase. The second integral is with respect to a deterministic probability measure, whose existence we guarantee and whose which is a tight sequence. And the measure mu p can be recovered via the log potential. So this kind of result in random matrix theory is known as the existence of a deterministic equivalent. So you can sort of say that the random measure mu p is equivalent to the non-random measure bold mu p, but we have not been able to prove that bold mu p itself converges. If it did, then of course the limiting spectral distribution would exist. And we ran out of steam after that, and as I mentioned, we have not met after the lockdown happened. So that's a pending agenda with us. Okay, and the measure mu p can be recovered by using the log potential. I don't want to go into that. I don't have time. And so we are working on the convergence of mu p, identification of the limit, relaxation of Gaussianity, which is heavily used in this model. Okay. So in other words, the non-null case is much more difficult, and that's why we impose extra assumptions of Gaussianity to deal with it. Even then, we did not get the convergence of the mu p, but only the existence of a deterministic equivalent. Okay, so journal references I've already given. I have not mentioned all the other articles because I wanted to keep it simple, but you will get all the references from by looking at these books. And that is the last slide of my talk. Thank you so much.
Yeah, Professor B.V. Rao had a question.
Yes, Billy.
So yes, I don't know if he can speak or should I speak. Can we make him? Can somebody allow and ensure that Professor B.V. Rao can open his? Or I have to read probably. Okay. So when gamma is bigger than 1, the distribution is on the annulus.
Yes.
Let now gamma go to infinity. Is there anything that can happen about the distribution or known about the distribution?
Gamma going to infinity would mean that p by n is going off to infinity. So that's like, it's a very good question. That's like, if you revert it, it's the same as dealing with the case that p by n goes to 0. I mean, you can, so the 0 eigenvalues of x star and x star x would be same. I mean, the non-zero eigenvalues, right? So for this case, there are no results. But for the symmetrized cases, the work I did with Monica, we have complete results for the gamma equal to 0 case. In other words, gamma equal to infinity, you can switch to gamma equal to 0. So for that gamma equal to 0 case, let me go back. So this works with Monica. So if you have gamma equal to 0, then you look at any polynomial, symmetric polynomial, then you have to center and scale it appropriately, and you will still get a limiting spectral distribution. Okay. One way of explaining that a little bit more is if you look at the sample covariance matrix, then you know that it converges to the Martingale-Pasteur law. If p by n goes to gamma, which is non-zero. If p by n goes to 0, then also if you look at S, the sample covariance matrix, you center it with the identity matrix, and then because most of the eigenvalues are going to 0 now, you have to scale it up. So the scaling up is done by square root of n over p. Then interestingly, you get back the same settle law.
I see.
So that would be an extension of
okay.
So this would be an extension of that result, which is known for this for the sample coherence matrix.
No, Arup, what I was wondering is,
Yes.
when your mass at 0 is 1 minus 1 by gamma, right?
Yes. Yes.
So as gamma goes to infinity, this mass will go to 1.
Yes.
So somehow I got the distribution.
Yeah.
It is outside on the annulus, but seems to come closer. And there is no indication that your annulus is coming closer to 0.
Yeah, you have to think a little bit about it, but you have to throw away the 0 eigenvalues, and if you look at the rest of it, then that should converge.
I see.
Yeah.
Okay, thank you.
So is there any question from those who are attending it live at ICER campus? Maybe they could just speak and maybe.
Any questions from the audience? Sir, I think there are no more questions. Sir.
All right. So let's thank Arup for this nice talk and nice introduction to this wonderful theory. Thank you.
Thank you.